All right, here we go with chapter 16. Chapter 16, we're going to break into two videos. First is A and B, then we're going to go C and D. We should be able to get through A and B real quick. The math is fairly lengthy on this chapter, meaning you only have a few problems for homework. The problem becomes is the math is fairly lengthy. Not incredibly hard, but it is lengthy and it is not the easiest. So let's jump right in. Start with chapter 16, electrical charge, electrical force. We're going to talk about electrical charge first. Electrical force will hold off for the next couple days. So here's your objectives. First, honestly, the first two should be fairly simple. Third one we'll talk about a little bit. It might be new information. But example, like charges repel, unlike charges attract. This is physical science, folks. You know this. Positive charges are called protons. Uncharged are called neutrons. Negative are electrons. Oh my goodness gracious, this is world-breaking information. Wait a minute, stop. Here we go. This is where we start talking about actually new stuff for physics. This is actually electrical charge is quantized. Again, if you remember from chemistry, quantized or quantum of energy is an actual chunk of energy. It's a fundamental unit of charge, meaning that's the brick or that's the amount you have to have. It's not like you can stand, kind of like when we had this discussion about stairs. You can't stand on the 2.3 stair. It just doesn't work. You're either on the second stair or on the third stair. Quantized. Either you have enough to get to the next quantum of energy or you don't. Now, the good news is charge is measured in coulombs. That's your C. Do not put a degrees C. This is where we start using all the other information that we've sat there and kind of ignored. Fundamental unit of charge, E. Fundamental unit of charge, E. It's measured in coulombs, but it's a unit of charge as E. So a single electron or proton is 1.602, that should be a comma, 176 times 10 to the negative 19th coulombs. Now, that being said, you will not use that number the entire time. I would say you write it down, make certain you have it in your notes, because that is what you will reference. That's what you're going to use. I'm going to take a step back, talk real quick about Millikan's oil drop experiment. We've already seen this experiment. You saw it in chemistry. We're going to go back to it. This is also one of the ways you can sit there and say this is actual how they calculated it. Notice on the left-hand side, the battery, the switch. The plate is in the middle, a charged plate with a pinhole in it. The bottom is a charged plate. This is how one of the ways they actually found the mass of these things, also the charge. In most cases, you already understand that. In fact, I think in your book you have reference to this. Page 560. You can read a little bit more, figure that out. Honestly, you can put your charges in there. Your book rounds it to 1.60 times 10 to the negative 19th. I'd actually use that whole number. Why? You have it. It's going to be in your calculator anyway. I'd use the whole number. So, electric conductor, material and charges move freely. We've already talked about conductors in the past. Insulator, charges cannot move. This shouldn't be anything new. That brings us to the next one. Insulators, conductors can be charged. An insulator can be charged. It's a little bit different. Conductors can be charged by induction. Basically, how induction works is you bring a material, any type, close to another charge. One of the ideas, if you think about your hand when you're running around in the winter, you build up static electricity on you. Well, guess what? You are now conducting all that or actually, the outside of your skin is actually conducting that charge. You've picked up the electrons. Now, you don't want to hold on to them. So if you go to that doorknob right before you actually send the spark across, right before, you're going to actually hold that, and the charge on your fingers is going to have the electrons built up, and then on the doorknob itself, the electrons, well, they're not going to be wanting to be right next to it, so they'll actually move away. This is actually called an induced charge. Induction, bringing it next to another charged object. My example, you're the charged objects. You are what's inducing a charge in the doorknob. Example, look, hey look, there's a charge. In this case, it's actually a positive charge. And look, the other positives are going away from it. Obviously, like charges want to repel. So in this case, you're induced charge right there. Cause of polarization inside the molecules. Molecules have positive and negative moving around. They're going to move a little bit. Can they move? Not really. Can they move a lot? No. It's just a slight induced charge. That induced charge is what we want to talk about. So, induced charge. Now, here's where it gets hard. We got to calculate the force. How much force are we talking about? This is where we're going to start getting things a little bit kind of crazy. So, electric force with gravitational force, can we actually make or devise a system where, I don't know, we can actually use levitation, where the electrical force is bigger than gravitational force? So far, the answer is no, or the answer is yes on an infinitesimal small scale. They've got aerogels that have been able to beat gravitational force. Problem becomes, when we put that on a large scale, not so good. Now, last one, apply the superposition principle to resultant force on the charge, find the position of. You're basically going back to the forces chapter on chapter 4, where you sit there and find what are the total forces on an electron. That's all it is. And I'll show you how to calculate it in class. We'll do the calculations in class. I'm going to show you how the question looks and the answer looks. So let's get right to it. So, Coulomb's law. The force due to an electric force is basically Coulomb's constant, Kc, charge of the first one times the charge of the second one over the distance squared. This is all we've already talked about this in some detail. This looks a lot like the force due to gravity. You guys can think back to the chapters 6 and 7. Force due to gravity, a constant times the mass of the first, mass of the second over the distance they're separated. Coulomb's law is actually kind of drawing on that. In fact, I'm not certain which one came first. I should probably look that up, but I'm not going to. So, resultant force. We're going to break this down to x and y. X, y, and z can be calculated as well. Most of our calculations will be x and y. So, vector sum of individual forces. Whoopie-doo. Short version, where's it going to go? That's all we're looking for. Forces is a simple way of doing a superposition. Equilibrium, the net forces on the body is 0. Again, if the box isn't moving, net force is 0. So, if the box isn't accelerating, net force is 0. So, example, this is what you have. So 3 charges. The first one is in the lower portion of your screen is Q1. It's a positive charge. Again, they give you the positive charge Q1 right there. Okay? Q2, another charge. Q3, another charge. Notice Q1 and Q3 are positives. If you look at the diagram, Q1 is a positive red, Q3 is a positive, Q3, there it is right there, and Q2 is a negative. Now, before you start adding any of this craziness, any of the numbers, any of the distances, any of that, you need to figure out what we're looking at. In this case, if I had those 3 electrons, I sit there and say, 1 electron, 2 protons. If I sat there and said, okay, what's Q1 going to do? We can calculate that. What's Q2 going to do? We can calculate that. What's Q3 going to do that? We're going to calculate. That's actually what we're going to calculate because that's what the question's asking. But you cannot calculate them all. Not at the same time. One's going to move. That's what we're going to calculate. The motion of, in this case, Q3. So if you look at it, go, okay, let's do the simple one. Q1 on Q2. Don't really care, to be fair. Q1 to Q3. They're both positives. Q1 is going to push Q3 away. If you look right above it, the force on 3 due to number 1. Sorry, I got a blue line. Now, in respect to Q2. So you have the negative and the positive. Oh wait, positive and negative, they're going to attract. So that's going to pull that way. Notice the blue line. So now I've got something pushing that way, something pulling that way. Right? All I want to do is find out where that particle, Q3 in this case, is going to go. This is breaking it down to Barney simple. That's what I want to do. I want to figure out where Q3 is going to go. In the end, through a lot of math, if you notice that there's 5 slides of math, I find a force in the y, a force in the x, and a force total, and an angle. That's it. And we're going to do a lot of math to get there. But if you remember chapter 4 and chapter 3, when we sat there, actually chapter 4, said a force going this way, force going that way, friction going that way, gravity going that way. All we have to do is sit there and break it down to x and y. Break it down to x and y, find the total in x, find the total in y, Pythagorean theorem, and the angle. That's it. I will tell you right now, I'm really simplifying that a lot. You'll figure it out in class. It's going to take a lot of math. The good news is, you know how you have 4, 5, 10 problems to work on? Typically, we'll probably get through 1 or 2. Why? 5 slides of math, that's a lot of math. So we're going to stop here. I would tell you, take a second, read through the book again. As always, most of this, honestly, inductors, conductors, charges, you guys should be pretty good at this. This is reaching back to physical science. Try and do the sample problems like they have. Write them in your notes. We'll go through the math. We'll get you started there.